So I decided to discuss today a bit more broadly magnetic power in various objects, rather than focus on a special, on a concrete topics, for example, neutron stars. And first, I'd like to remind you that the universe is full of transient events, right? And that's what time domain astronomy is about. Here I just is a little collection of things that are flaring and producing really bright transients, which range from fast radio bursts, these are radio transients, to gamma ray bursts. We see, for example, flares from blazars. We see, of course, bright flares from magnetars. We see bursts from merging neutron stars together with the gravitational waves by now. And so in this picture of bursting universe, magnetic power plays a special role. And in fact, when you look at these objects, one common feature is that they are believed to have magnetically dominated outflows or coronas or magnetospheres, that is, places which are very strongly magnetized. What I mean more specifically by plasma magnetization is this parameter sigma, which is the ratio of, roughly speaking, magnetic energy density, b squared over 4 pi, well, 2 times magnetic energy density, divided by the rest mass of the plasma. So sigma can be much greater than 1 in these objects, for example, in jets, or certainly in the magnetospheres of neutron stars. And one simple initial point is that these bursting phenomena are particularly bright. The suspicion here is that it's particularly strong when sigma is much greater than 1. If you like to think about this sigma in terms of plasma physics, if you like plasma physics, then the same quantity sigma can be thought of as the ratio of gyro frequency squared, defined here, and plasma frequency squared. I hear some little noise in the background. I think someone is not muted, I think. I don't know who he is. Yeah, I hope it's not disturbing. Okay, so, all right, so these systems have a lot of magnetic energy per particle. So if magnetic energy is going to be dissipated, particles will accelerate like crazy and produce bright emission. Another special feature is that basic wave modes propagate in this medium, in this magnetized plasma, with speed of light, essentially. In particular, familiar alpha waves in MHD, they propagate with this speed, which basically becomes 1 in the speed of light units. That also means that the characteristic time scale, let's say causality time scale of the system is basically light crossing time. So something can happen really quickly in this system. In particular, dissipation could possibly, in principle, happen even on the light crossing time scale. So far, it's unclear why it would happen, but energy can relocate very quickly in these systems. Okay. Here is one example. It's a canonical example. Of course, the places with strongest magnetic fields are neutron stars, and this is one bursting magnetar. You see the history of bursts, how the system is active for many years. Here are years. Typical burst has duration of 0.1 second, luminosity up to 10 to the 42 ergs per second. Most of the energy output is in tens of keV range, hard X-ray band. And sometimes, like here in December 27 of 2004, it can go giant flare. and then luminosity jumps up to 10 to the 47 ergs per second. And so what are these? These are the events of very fast, very efficient dissipation of magnetic energy on very short time scale, right? So that's basically what's happening in these systems. So it's clearly I mean, we know these canonical examples, magnetars, where magnetic dissipation is known to be very fast and very efficient. Similar processes can work in other compact objects, and the reason to believe why they can be powerful, well compact objects. Well, if you look at magnetic fields as magnetic flux divided by characteristic area of the object, r squared, r is the size of the object, then if you think in the simplest way of how this magnetic field came about, if this compact object used to be a star with some magnetic flux and it collapsed, conserving the flux, magnetic field was amplified to large values. Actually, it could be amplified even more by some kind of dynamo. Then what would be the luminosity of a burst that happens if the energy is released on the light crossing time? That would be the luminosity. Magnetic energy squared times the area squared times the speed of light. And you can see that this luminosity scales as 1 over r squared. The more compact the object is, the more powerful burst you will get potentially from these objects. Here's a little list of different fields and different compact systems. Black hole X-ray binaries, 10 to the 7 up to 10 to the 8 Gauss, pulsars up to 10 to the 13 Gauss. And these most dramatic systems, magnetars, GRB, central engines, neutron star mergers, their fields around 10 to the 15, 10 to the 16th Gauss. And by the way, I have this extra column in this table that shows the values of the gyro frequency. You can see how huge this frequency is, right? Especially in neutron star systems and GRB central engines. Okay, so the question here is that, so I'd like to discuss kind of what are the common mechanisms potentially working in these systems. Actually, we don't have a big menu for this mechanism. When you have magnetic dissipation, it's got to be executed by non-ideal electric field. So what I mean by non-ideal, it's in contrast with normal ideal MHD. We got used to think about ideal MHD as, which is usually a good approximation for astrophysical plasmas, is basically the system where fluid, which can conduct currents, can move with some velocity v, but in such a way that the electric field in the rest frame of the fluid is 0. So it's kind of screened. This is what we call ideal MHD. So E prime is the electric field in the rest frame of the fluid. So this screening requires two conditions, which seem very easy to satisfy. One, you got to have enough plasma particles to screen electric current. What is this minimum density? Is the current density that you need to sustain curl B, whatever curl B is in the system, whatever MHD wants, divided by electron charge, divided by the speed of light. And if you estimate J naively just taking curl B, which is B over R is the size of the system, you can rewrite this condition in terms of this magnetization prime to sigma, gyro frequency, and the light crossing time. And you will see that because gyro frequency is so huge, let's say 10 to the 20, like examples I showed, and the light crossing time may be millisecond, 10 to the minus 3 seconds for a compact object, you can see that it's very easy to satisfy this condition. I mean, you would need enormous sigma to violate. So there is enough plasma in most systems. Not always, by the way. Sometimes you do have charge starvation, but it's easy to satisfy. And the other condition is negligible resistivity. And again, astrophysical plasmas, especially in compact objects, they're completely ionized, and usually collisions are not important, really. So collisional resistivity is small. However, when you look at systems that evolve because they are stirred, let's say if you perturb magnetosphere of a neutron star or accretion disk corona or a jet, they tend to develop turbulence cascades. And so what happens in these cascades? The energy is in magnetic fluctuations is transported to smaller and smaller scales, and eventually it comes to the dissipation scale. Okay, so it turns out that the dissipation scale is typically just this speed of light divided by the plasma frequency, which is microscopic. What happens in this scale, basically, in particular for alpha wave cascade, the energy, the evolution is very much ideal. It's like ideal MHD at large scales. And then you develop Kolmogorov-like spectrum, a parallel spectrum of fluctuations of alpha waves, let's say. And then they come to that scale, they become Landau damped. That is, these waves become to be absorbed by particles. The time scale for this dissipation to develop, that is to absorb whatever power you put in driving the cascade, whatever is the mechanism for driving the cascade, let's say you over twist the magnetic field lines and you create some instability and MHD instability. It's initially all ideal, and then it develops this cascade. It develops on a time scale which is comparable to the alpha wave crossing time, which is again light crossing time in these high sigma systems. So MHD turbulence is one way of fast dissipation. And of course, it's an enormous topic of studies historically for non-relativistic MHD. For ultramagnetized systems, it's less studied, but by now there are, especially recent papers, there are several papers on this topic, and including first principle simulations of MHD turbulence, which follow particles, plasma particles individually, and you can watch in this simulation how the cascade is developing and how the energy eventually is transferred from alpha waves into two particles, reaching this dissipation scale. So the usual, well, the technical, I'm not going to give you more details about it, but just to say the way it's simulated, I'm sure Sasha, I mean, in CCA, there is significant research program on that topic, how you can simulate plasmas from first principles. So you can use so-called particle in cell method, where you follow electromagnetic field evolution self-consistently with individual particles. So you follow particle motions in electromagnetic fields, and you calculate the current that these particles produce, and you use this electric current as the source term into Maxwell equations. So that you get this closed system, you can evolve it in time from first principles. Okay, the interesting question here, which is currently debated, and I decided not to look too much about it. The interesting question there is how exactly particles accept this energy that is given at the dissipation scale, and whether you get non-thermal particles from that. Once it's interesting to know the spectrum of particles that come from the dissipation, because then they begin to radiate, and you can predict what kind of emission you should see from the systems. However, what is even less explored is this, I think, important point which I would like to make here, is that in fact, for cascades developing in the brightest bursts, the plasma becomes optically thick. I will explain in a second why. And then the fate of the cascade energy is actually changed. The dissipation mechanism is changed. So this figure shows the fluctuations spectrum, let's say Kolmogorov spectrum. At large frequencies, you have ideal MHD and just normal turbulent spectrum. The collisionless damping, this is the damping on the plasma scale that happens, is shown by this red line. So you start with very large scale, and the cascade goes all the way to very small scale, which is not even shown on this plot. It's somewhere, it's magnitudes smaller than the size of the system. However, if the cascade develops in optical thick plasma and it is radiatively efficient, that's the case of the brightest magnetic burst that we see in the universe, then there is Compton drag on the edges, something like similar to silk damping, basically, in the universe. And it can terminate the cascade before on a scale which is much greater than the microscopic dissipation scale. And this is what's shown in this bottom panel here. Basically, it's the comparison of the time scale to past energy in the fluctuation from one scale to the smaller and smaller and smaller scales. So this cascade time scale is shown here versus the scale, 80 size, which is normalized to the photon free path in the system. It appears precisely because we're talking about radiation damping. So of course you can damp the turbulence if it becomes not, if it's not too optically thick on that scale, because otherwise radiation is trapped and follows the turbulence. But just like silk damping, when you start diffusion between across the scale, then you can damp this motion. So the point is that when your system is optically thick and the critical optical depth is not far above unity, it's comparable to unity roughly, then dissipation doesn't even have a chance to develop on microscopic plasma scale. Instead, it disappears on a much bigger scale. And there are not many simulations, but hopefully there will be soon to show what happens then. Now, why these systems are optically thick in bright bursts? In the brightest burst, let's say. The physics of here is very simple. When you have a lot of power in a small volume, then you easily create electron-positron pairs. And the key parameter that determines whether you create a lot of pairs or not is so-called compactness. It's defined here, energy density U in the system. Let's say magnetic energy density, radiation, they're usually comparable if you have efficient dissipation of the magnetic field in units of electron rest mass times Thomson cross-section times the size of the system. So this dimensionless parameter L varies from say roughly 100 for accreting black hole, let's say Cygnus X1 in the central region that emits hard X-rays, to huge values like 10 to the 13 in GRBs. So it can be really big. And when this parameter is big, then it's easy to use a small fraction of photons, even a relatively small, I don't know, 1%, for example, of photon number, that end up above electron rest mass, they easily collide with each other and turn into pairs. So when this parameter L is high, as was shown back in the 80s by Rollins-Svensson in particular, then the plasma easily reaches annihilation balance, and its optical depth is given by this expression. So L is the compactness parameter, and Y is so-called pair yield. It depends on the details of the spectrum, but it's typically 0.1, maybe 10 to the minus 2 in some systems. But you can see when L is huge, the optical depth has to become large. Okay, unless there is a reason to drop this Y parameter, which this pair yield parameter, which does happen in some cases. I will show you an example. Okay, so that's basically what's happening in bright bursts. Which have high compactness parameter, they dress themselves in electron-positron plasma, and therefore the dissipation develops an optically thick region in this brightest burst. Okay, so after these general remarks, let me just show one specific example, which illustrates that to get strong turbulence and fast dissipation, you don't really need dramatic stirring of the plasma. So in particular, well, in this example, it's a neutron star, and it has, let's say, initially dipole field. And suppose there was a star quake with a small amplitude. This is the simulation that was done by Ashley Bruns-Crowe of the simulation of the star quake and how this motion of the neutron star couples to the magnetosphere. So what color will show in the simulation is the magnetic field component that is perpendicular to the plane of the sphere, the toroidal magnetic field that will be excited by the toroidal oscillations of the star. And so what you will see here is that, yeah, you launch alpha waves. You don't see by eye here the oscillations of the star, but they are small. They have small amplitude, something like 10 to the minus 3. The star quake also spreads through the crust, and you see more alpha waves populating more and more the magnetosphere. So what you see in this simulation is a simple fact that alpha waves actually grow as they propagate along extended field lines. Delta B or BH, one can show this easily to conserve the flux in the wave. It should go as r to the plus 3 halves for the dipole field. And so even though the initial delta B over B is small, 10 to the minus 3, at let's say waves that reach tens or 100 radii, they become very large amplitude waves. And it's very easy to have strong turbulence in these systems. Furthermore, besides the turbulence, there is another mechanism that is easily activated. And that's the second mechanism that I would like to talk about. This is magnetic reconnection. So this is the simulation that maybe you've seen before. Siaji did it at CCA. This is an example of similar problem. You have, just to illustrate how you have a small star quake with amplitude maybe 10 to the minus, on this example, 10 to the minus 3. And as the wave propagates to larger and larger distances, you can focus on the second panel, you will see the magnetic field lines that are shown by a line will become deformed. The alpha wave deforms them. And there is a magnetic blob that actually leaves the star. And behind it, in the tail of that blob, you see magnetic reconnection. The field lines reconnect. This is a dissipative process. Then you see a second blob. In the simulation, there are 2 alpha waves launched. And again, it grows in amplitude, and the magnetosphere kind of spits this blob of magnetic energy and drives a large-scale explosion, actually, from this star. But for now, I'd like to focus just on this region. So you see that the magnetic field behind even a small amplitude quake of the star can trigger large-scale, strong magnetic reconnection on a large scale in external external magnetosphere, in the outer magnetosphere, let's call it radii, about 100 radii of the star in this example. By the way, if you would like to ask any questions, please just stop me. It would be even better. I'm completely okay if you interrupt me at any point. Okay, you don't have to wait with the questions till I stop.
I assume there's a 2D simulations, right?
Yep, this is 2D force-free simulation.
Okay, so I believe that in 3D you may have a different picture, right?
We are working now on 3D. It depends on how you drive it. So yes, you can 3D, you can actually get different stuff.
Okay.
A little bit. But the basic idea that the wave can break the magnetosphere through this growth of the wave and eject a chunk of magnetic energy is rather general.
Yeah, but ejection would be different in a 3D turbulent magnetic field, right? Yeah. Okay.
All right. Okay. So this is a schematic picture of this important process of magnetic reconnection. It shows how the well, it happens as just shown in the case of alpha waves driving magnetic explosions. But of course, similar thing happens if you do this slowly. And in fact, this is the preferred model for giant flares. That's what we think are happening in giant flares in magnetars. And similar things probably are happening in accreting black holes and the coronas of accreting black holes. When magnetic field is over twisted, it tends to inflate And as it inflates, it pinches. This inflated part is a pinching process, and then you form this very thin current sheet. So high sigma in particular, but in general, ideal MHD is actually prone to this process of forming very thin current sheets. It just collapses. It's called, this phenomenon has been special name, magnetic collapse. When two magnetic field lines, two opposite fluxes come close to each other, boom, they flatten. They like to flatten. They form a thin current sheet. Just it's pure ideal MHD dynamics. And then what happens is that this current sheet becomes unstable to reconnection. The same process it has to happen if you have magnetized neutron star binary, which of course have some magnetic field lines connecting the two stars. And when the two stars rotate about each other, and they also have some differential rotation, so they're not synchronous. So that was simulated by Elias Most and Sasha Filipov, and they saw this similar phenomenon of beautiful inflation of over-twisted field lines and pinching process, again, forming these current sheets. So let me now focus on what's happening here, how energy is emitted from this region. And of course, the analogy that all of us know is a solar flare. Let me show one picture of solar flare. It's big flare, nice color. You see magnetic field lines. So we know magnetic reconnection does work in the sun. Okay, but in that case, what's the power of the solar corona? It's like millionth. It's nothing of the solar luminosity. But here, in the case of these systems, it's extreme power, and actually it's the dominant form of energy release in the system. So what's the basic process? You have two opposite fluxes, magnetic fluxes. You have current sheets sustaining this jump of P0, and a number of people simulated this using particle and cell first principle kinetic simulations. So what's happening? There is so-called tearing mode. This current sheet breaks up into threads because currents like to attract. So there is this tearing mode, instability. And then the plasma begins to, when you see this, they break up into plasmoids. These plasmoids start to move around, merge, and they continually produce new plasmoids. So you break MHD here in an interesting way. You break it immediately on small scale. The sheet has become so thin that basically a Larmor scale of particles that that you come to the scale where ideal MHD doesn't hold, and then the steering mode causes dissipation in that system. So you don't even need the cascade, you immediately come to that scale, and then you actually can build bigger plasmoids through, and you can turbolize them if you have in 3D, actually, you can start to move around. Okay, so again, a large body of work here, but I would like to make a similar point, just to draw analogy with turbulence. When you have magnetic reconnection in a compact object, Cygnus X1, gamma ray burst, a neutron star magnetosphere, you've got their dense radiation field. And so the process of energy release then changes, okay? So and I can explain very in simple terms what the change is. So basically, the magnetic field lines, as you see here, you can think of them like strings. They reconnect, they snap here, and they pull chunks of plasma with them. They accelerate them to relativistic speeds in highly magnetized plasma. Now, if this process works in radiation field, then there is a resistance to that process, which comes from the drag imposed by radiation. So this plasma upscatters whatever the ambient photons are, and effectively the magnetic energy goes directly from through the plasmoids, but it goes directly into photons. Instead of hitting individual particles, you mostly pass energy from the magnetic field into upscattering photons by bulk motions of big chunks of plasma. So again, you remove energy from the system mostly on large scales, much greater than the microscopic scale. Okay. Yes, there is also X-point formation. There are particle acceleration processes, but a large part of energy actually goes through this large-scale motion upscattering background photons. Another thing that radiation does, of course, it keeps the plasmoids cold, because in these systems, the cooling time scale is actually much shorter than the light crossing time scale. The ratio of T cool to light crossing time, S is the size of the system, whatever, let's say, Schwarzschild radius for a black hole, or radius of the star for a neutron star. The ratio of the two time scale is roughly 1 over compactness. So it's tiny. Okay, so this cold pieces of plasma pulled by magnetic field lines through this kind of viscous background, and it's a dissipative process that way. Another thing that happens here is that this process of quantization of photons brings them easily above electron rest mass, and they start to collide with each other and produce electron-positron pairs. And this layer, the connection layer, dresses itself into pure plasma. I will show a simulation that illustrates how this happens in a minute. So this is a measurement from the simulation, particle in cell simulation with radiative cooling, where the cooling rate was just chosen. Radiation field was imposed by hand, and we looked at different cooling rates and run many simulations with different cooling rates, otherwise identical simulations. The same reconnection setup, same magnetic fields initially, but different density of background radiation. So when no cooling, in the no cooling limit, no background radiation, 90% of energy is given to individual particles, and only 10% goes into this bulk motion. As you increase cooling rate, it's the other way around. About 80% of energy goes into bulk motions, and it's immediately removed from Compton scattering in this case. And 85%, and about 15% goes to individual particles at so-called X points. Okay. Well, it's just actually, it's a side remark I wanted to make. I'm mostly focused in this talk on transients, but actually it may be that systems that we think about as persistent sources, for example, Cygnus X1 and the hard state, it actually, it seems, I think we're likely not resolving the steady emission, which is actually composed of very short flares. In fact, there was an observation in Cygnus X1 by Gerlinsky and Jarsky in 2003. I think there was a paper when they caught a flare, they were able to resolve in the data. They found a millisecond flare, which was 20 times stronger than the average flux. So the point of this slide is that maybe that hard state black holes that we observed produce the emission through many superimposed magnetic flares. And this slide shows that the spectrum predicted by this radiative magnetic reconnection, which I just described, shown here in the upper panel, is actually quite similar to the hard state spectrum of black holes. But I want to come back to neutron star systems, which produce much brighter bursts for the simple reason luminosity scales as b squared. Neutron stars have much stronger magnetic fields. That's why they are so efficient bursters, so bright. And I would like to show another simulation which actually addresses a simple problem formulated in this way. So what is magnetic bursts in let's say, magnetic reconnection burst. Essentially, you annihilate opposite magnetic field into ultimately into photons, right? That escape the system. And also they're capable of producing electron-positron pairs. This problem has one parameter, which is dimensionless, so-called magnetic compactness. So you're given the magnetic field, and you are given the size of the system, yes? And you can define, it can take magnetic energy, the initial magnetic energy, times S, that defines this dimensionless compactness, and that's about it. That's all you have. Well, an additional parameter is how quickly you dissipate this magnetic energy, but we know it's, let's say, for magnetic reconnection, it's about 10 times light crossing time of the system. So the question, it's a very well posed problem. You have annihilation of magnetic energy into heat, and you want to know what is the spectrum of the burst. It's a theoretical question, but you can compare the spectrum with actual observed bursts, for example, with magnetar bursts. And I would argue that would be the prediction for magnetized neutron star mergers, because the process here is exactly the same as in magnetar bursts. Okay, I did a little simulation. Well, actually not so little. It includes all the radiative processes that you need in this system, but it mimics the reconnection process by basically damping energy with a given spectrum of particles, and I played with different spectra. What I wanted to follow is how the system self-organizes to radiate, and what self-consistent radiation spectrum will be in this way. It will find, it will be able to emit, let's say. So there are a few simple conditions that actually determines the physics of energy release here. One is energy balance. Whatever energy you damp, it's magnetic energy, it has to immediately convert to radiation because the cooling is so fast. So you have instantaneously, you have energy balance at each moment of time. Then you also have the electron-positron annihilation balance, because the annihilation timescale is shorter than the light crossing time here. You form the photons that you're going to produce, and the simulation does the radiative transfer. It follows each individual photon, how it can tries to escape the system. It may scatter for electron-positron, or it can collide with another photon and turn into electron and positron pair. So these processes are followed numerically through Monte Carlo. This is kind of nonlinear radiative transfer when you don't know the scattering opacity in advance. You don't know gamma-gamma, photon absorption opacity in advance. You have to evolve it self-consistently. But the beautiful thing here is that it actually self-organizes, and it's time-dependent simulation. You do see how it self-organizes and how it respects the energy balance, like positron balance, and the photon balance. That's the third condition that is respected by the system. These pairs that are produced, they generate photons through normal branch trunk, double Compton scattering, but mostly through synchrotron, synchrosynchrone radiation in the magnetic field. And so the number of photons that you produce is the number of photons that eventually escape, of course. This is the result of this evolution that shows the energy per photon essentially is effective temperature. And one can see that for various values of this compactness parameter, relevant values, which are high for magnetar bursts, the energy per particle is basically 0.1 mc square. Okay, it's the units of rest mass. The reason why it's self-regulated, close to this 0.08 plus minus 0.2 is simply, I mean, you can think about it this way. If you start to increase temperature, then you create many more electron-positron pairs because the tail of the radiation spectrum goes above mc square. You have more pair creation. Then you begin to produce more photons by these pairs. And this enhancement in photon production cools the plasma back. That's how the self-regulation loop works in the system. You can also calculate the position of the photosphere. So this is altitude, Z is the vertical axis here. And this is the heating region, H. And you can see that the density is a function of altitude. And you see a lot of pairs produced outside the heating region. And you can find the position of the photosphere, which increases, altitude increases with increasing compactness, but not dramatically. And then you can look at the spectrum that escapes. And the spectrum, right, I don't want to go in details, but depending on the assumptions of the particle spectrum that you inject by magnetic reconnection, you can have slightly different spectrum. But all of them basically peak between 30 and 80 keV. So it's a hard X-ray band burst. So the robust result of this simulation is that the system dresses itself into optical thick electron porcelain cloud. And two, it produces hard X-ray burst. And this is more or less what we see in magnetar burst. It's an example of an observed spectrum. You can see here that it peaks at tens of keV. It should also be predicted, basically it should be expected from neutron star mergers if you deal with magnetized neutron stars. They should emit the same spectrum because this system is its radiative properties should be no different from magnetar bursts. It's similar magnetic field, similar sizes, 10 to the 7th, it's all about the same. So these two neutron stars, as they merge, before they merge actually, before the gravitational wave signal, they should be quasi-periodically producing these flares with this kind of spectrum, and which would peak at about 50 keV. Okay, all right. So I wanted to say a few words about the topic, which may be familiar to almost all of you. So maybe I should go quickly through that. It's fast radio bursts. Well, it's one of the biggest discovery in modern astronomy, certainly in radio astronomy after pulses. It's the biggest discovery, gigahertz bursts with millisecond duration. They occur in distant galaxies, localized at significant redshifts. They have high luminosities in radio band. There's a huge luminosity for radio band. The rate is huge. If your radio telescope has tiny field of view, but if you extrapolate what you should see for the entire sky, it's more than 10,000 bursts per day. So these bursts, there are different models for these bursts, but I think there's convergence to, I think most people do believe that they come from it's magnetic phenomenon. It's driven by some kind of magnetic dissipation or release of magnetic energy. And actually, from the early days after the discovery of FRBs, they're associated with magnetars because magnetars produce bursts with similar rates, and bursts have millisecond duration, so that indicates a compact source. And naturally, you would think about a neutron star. So there are different versions of proposals about how magnetars could produce a burst. Let me just tell you what is my preferred scenario for that. I think it's a blast wave. I showed Yag's simulation where even small perturbation of magnetic field can can expel a plasmoid. But certainly giant flares do that. We know from observations. The same famous giant flare that I showed in the beginning in 2004, it did produce significant ejecta. Well, the observation showed mild relativistic ejecta, but they should be ahead of it. There should be ejection of just magnetic energy, which has huge Lorentz factor, just free expansion of pure magnetic energy, almost pure. Initially, it has some electron-positron plasma for sure, but as it expands and cools down, the plasma annihilates, and it basically pure magnetic energy, which develops huge Lorentz factor, like 10 to the 5, one can show. And then this energetic magnetic plasmoid has to sweep up the whatever the external medium is, and the external medium is the pre-explosion wind from the magnetar. The parameters of this wind are not so well known. I tried to estimate it, and this is my best guess for these parameters. This magnetization of the quiescent wind, like normal spin down wind from magnetar, is the Lorentz factor. And so when you drive a blast wave into this wind, you emit something that is compressed by the Doppler factor of this blast wave to 2 millisecond duration, basically. So that's the complete analogy, well, complete except for the huge Lorentz factors with the blast waves in the solar wind from magnetic flares in the solar corona. So here you have very high gamma pre-explosion wind ahead of the blast wave has Lorentz factor, let's say 20. The blast wave Lorentz factor is found from the pressure balance between the piston, the magnetic plasmoid that drives the blast wave, and the run pressure of the upstream wind. And so the ratio of the two is about 100. Typical parameters I put in here, giant flare luminosity, and this is roughly estimated wind power ahead of the blast wave. And the mechanism that is known to work in this scenario is the shock maser mechanism that's got to produce coherent radio waves. So it's just to quickly explain what it is. What is the shock, first of all? The shock is a jump in the magnetic field. And you have particles that cross the shock and begin to gyrate. That's how the shock is mediated through Larmor rotation. And this is the slice from the simulation and the velocity space. You see this ring structure in the velocity space. This is gyration about this magnetic field lines. There is a cold stream that comes in, crosses the shock, and begins to gyrate. And so this ring is unstable and to bunching, and that's what's so-called maser mechanism. And it begins to radiate coherent waves, electromagnetic waves, with frequency equal to the gyration frequency, approximately, not within a factor of few. So this coherent emission mechanism produces radio waves. It should produce radio waves, and this is a specific mechanism that can work. I mentioned should work in whenever you drive a magnetic explosion from a neutron star. Its shock should produce a low frequency coherent emission whose frequency depends on radius and passes through the radio band at about 10 to the 13, 10 to the 14 centimeters. Okay, now this is one development. I'm sure you've heard about it, but I have to show these slides. The discovery of an FRB from an actual magnetar in our galaxy during X-ray burst. So you can see two radio peaks during the X-ray burst, a little bit leading the X-ray peaks. They have millisecond duration here. So now we don't doubt that magnetars are capable of producing FRBs. And it seems really likely that cosmological FRBs can also be associated with magnetars. Okay, well, I'll say just briefly, another discovery that from radio astronomy, observation of FRBs is the periodicity that one of repeating FRB sources have shown. Actually, there is another one also with longer period. So in this case, it's 16-day period. So you see active repeating source of fast radio bursts, then it disappears and then it reappears again. And this onset of activity has a 16-day period. And one possible explanation, which I don't go into detail, is the precession of the source. So if you have a magnetar, which is hot enough to be not superfluid and also deformed by the magnetic stresses, then at a level which corresponds to a field of about 10 to the 16 Gauss, the expected fields of magnetars, then you expect to have precession of this object. And so if this activity is not isotropic, which is likely the case if it emits, let's say, blast wave with some solid angle, it can precess out, its activity can precess out of the line of sight, and then it will come back to the line of sight. And that's how you can explain this. Can explain this effect of periodicity. Okay, I have a few more minutes, right? So I can say a few words about new stuff that I don't think maybe Sasha has seen it, but not anyone else. So collision of relativistic alpha waves. So it's another mechanism which is actually different from reconnection. It's a very fast way of dissipating magnetic energy. Let me explain what it is. This is the setup of the problem. You have, it's idealized setup, but that you expect to see when you have, let's say, neutron star, for example, a magnetic sphere, and you launch an alpha wave. It reflects from the surface of the star and goes back, and you have the wave colliding with itself. But in more general situation, when you have two alpha wave packets and they're colliding, they're moving toward each other and colliding. Because we deal, normally nothing dramatic would happen, okay? Because normally in non-relativistic MHD, nothing dramatic would happen because electric fields are small compared to the magnetic fields, non-relativistic MHD. For relativistic alpha wave, electric field is equal to electric field of the wave. Here is actually equal to the magnetic field of the wave. It's another way to say that the wave propagates with the speed of light, essentially. So when these two waves collide, if you naively superimpose them and they have opposite polarization so that their magnetic fields cancel out and the electric fields add up, you will see E larger than B. This would be very dissipative because then the electric field would just start to accelerate particles as it wishes. It doesn't care about magnetization anymore. It begins to drive particles with higher and higher momentum across the magnetic field. In reality, what happens, and that's what is seen shown also by peak simulations, is actually ceiling for the electric field, which is imposed by the background magnetic field along which this field, these waves propagate. So this x-axis is the direction of the background field. The wave has perpendicular field, as always, for Alvin waves here, right? So these are two simple Alvin waves that don't have any k-perp. It's the simplest possible configuration. They propagate along, the k vector is along the background field. This is the electric field. Background field B0 along x, and there is by and ez, the simplest possible Alvin wave. So when the two waves overlap, electric field doesn't quite add up. It goes to this maximum set by the value of the background field. By by symmetry is 0. The wave field vanishes, and there is only background field at the center. So what's happening at the center is effectively you impose this boundary condition. It's like imposing a wall from which the two waves will reflect, and they reflect with a smaller amplitude, A-1. As you can see from, you can show from this boundary condition. So in the end, the result of collision is very simple. Its reflection would be reduced with amplitude reduced by 1. Amplitude is delta B over B here. And the fraction that is absorbed at the center, at the collision center, is 1 minus this ratio of A-1 squared divided by A squared. Right? It's, A characterizes delta B, A squared characterizes the energy of the wave. And it's maximum when A is 1. So when you collide two symmetric waves with delta B over B equal 1, then actually 100% of energy is absorbed. So the waves just annihilate each other. Okay, so that's what's happened. That's actually really funny, that the energy just disappearing. They annihilate each other. Where does the energy go? It goes into particles. The peak simulations beautifully confirm this this relation. Okay, this absorbed fraction. These are several. It's done by Xinyu Li. It's about. We will publish the paper, so it's not published yet. But he did a set of simulations, both 1D and 2D, and found that for the most interesting case, when A is like 1, when the efficiency is 100%, it's really 1D system. You don't worry about even 2D aspects. There is no tearing instability. It's not like reconnection. The dissipation process, it does not involving any tearing of the current sheet that forms during this collision. So here, when the two waves collide, there is a jump of B, and you form a current sheet. This is where dissipation occurs. Okay, and to finish, let me show well, a couple of slides here. So one is the movie. You see here the horizontal axis is just the position of x-axis. 0 is the center of the collision. And if you focus on the upper panel, this is the Lorentz factor of particles. And color, well, color just a way to highlight particles that are moving here. Colors corresponds to the initial position. You can see particles drift in, then they accelerated in the current sheet with some oscillations, and then drift out. Okay, so this gamma is basically like a squared times sigma, the magnetization of the system. In this simulation, this magnetization was 20. So this system is, well, I probably should skip this. I should just say that how these particles are moving here in this dissipative current sheet can actually be understood analytically. If you go to the right frame, you can reduce this problem. I was planning to talk a little more about it, but maybe it's even better. I don't have time to explain this problem, but you can reduce the problem to simple mechanics, motion in two-dimensional potential, and two-dimensional motion with some effective potential, and basically understand how particles enter, exit this current sheet, drawing an analogy with the valley, with the curved valley, essentially. Anyway, so this is the summary of this mechanism. Pointing flux comes in, what comes out is energetic particles after this dissipation. And energy is disappearing with the speed of light. So the net result is that 100% of the wave energy annihilates on the light crossing time scale. And what you get instead of wave energy, you get cloud of hot particles with Lorentz factors about sigma, magnetization. And this cloud is spreading with velocity in the x direction, plus minus x direction, with speed c over gamma. And density correspondingly is compressed by a factor of gamma. That's what this dissipation mechanism does. Okay, let me go to my conclusions. So to summarize, so I was talking about this high sigma system, some general mechanisms that should be at work. And if you compare it to what you would hear in talks, I don't know, 10 or 20 years ago, nowadays you hear different, much more, I think, interesting stuff, hopefully, because there's an enormous step done now in understanding plasma physics, specific concrete mechanisms that are at work there, producing energetic particles and radiating the emission that we see. Before, the models were more phenological. Okay, so you just assume that you dump energy in some form, and then you try to do some radiative physics, and that was really difficult. Now, one point I want to make is that very simple point is that high sigma magnetic fields live really dangerous lives. I mean, because this ideal MHD, if you don't touch it, it's okay, but it's sufficient to torture it a little bit, and it quickly pushes itself beyond its limits. It goes outside the MHD realm, and it could do it through turbulence cascade. When you come to small enough scale, become to dissipate, for reconnection, or you can collide two ideal waves, but when they begin to touch, if they're relativistic, boom, they just annihilate each other. So relativistic MHD is prone to very fast dissipation. That's like fundamental point here. Second point is that when you look at these brightest bursts, like magnetar flares, for example, then they're cooling, very much cooling dominated systems, and they inevitably lead to huge percreation. Well, when they're bright enough, then they even become opaque. The plasma that they create becomes opaque. And what needs to be done next is to, of course, is to try to understand these kinetics using first principle plasma simulations to see what kind of distribution functions these systems produce. So why this is important? Because it's non-thermal particles that can come up, can still be generated in these radiation-dominated systems. They affect the photon production rate, the photon number that eventually comes out from the burst. These photons are quantized. And I talked briefly about possible mechanisms for FRBs, which are blast waves from these magnetic explosions, in particular magnetar winds. If finally, if we expect to, if we hope to see a precursor from neutron stars, our best hope would be that they're magnetized. And if they're magnetized, the best band to look for emission is hard X-ray band, because then they should be, there is a good reason to believe that they should produce like 50 keV emission, let's say 10 to 50 to 100 keV emission. And I'll stop. Thank you.
Thanks, Andrei, for the great talk. Let's have your questions now. Ike wants to ask a question.
Well, actually, there was an applause, but I can ask a question as well.
Sure.
I had this question on the alpha wave collision with the plot you showed, where you have the dissipation versus the one that one. Mm-hmm. So at some point it seems like the tearing mode kicks in. So is there a rule of thumb to understand what time scale should be comparable to tearing time scales for this to kick in? Because the Alfvén crossing time scale doesn't depend on the A, right? Doesn't depend on the amplitude much.
Right. So the way we actually look at it, the size of the Alfvén wave packet that is colliding is macroscopic compared to the thickness of the current sheet. So the thickness of the current sheet is basically plasma skin depth. One can show that, which is really small. While usually, for example, if you think of Alfvén waves that come from Stark wakes in magnetar magnetospheres, they have frequencies in kilohertz range. So these are long waves. And so you can think of that system, of this dissipation process as quasi-steady process. Okay, so you have two macroscopic packets, they start to collide and annihilate each other, and this process occurs quasi-steadily. So you either have tearing instability or not, but there is and you don't, like in this case, sigma of 20, when you have A is equal to 1, you don't have it. And you do have it when you have, not surprisingly, by the way, if you have very large amplitude, if you keep increasing amplitude of the wave, what does it mean? Delta B becomes bigger and bigger than the background B. Well, in that limit, you just forget about the background B and you have two opposite fields. It's pretty much the standard reconnection problem. And in that way, you do expect tearing mode. In other words, it's not stabilized by this cross-layer field. And that's what we see here in two-dimensional simulations, that you begin to you have normal reconnection. However, there is just one point is that even when you have tearing mode, it could saturate at a low level, and maybe indeed does not. It means even when you have tearing stability, it may not be so critical for the system. So there is smooth transition that is happening here.
Is the wave even stable at these amplitudes in peak codes? I mean, the Alfvén wave,
isolated wave. Yeah, I mean Chinyu starts when they almost touch, but you could start early. They should be stable. Yeah, I mean, yeah, it's basically they are force-free waves. At such sigma, you can forget about plasma inertia. They propagate with the speed of light. If you have just one wave, it's stable and it's good. Nothing happens. No dissipation. It's only when you have collision that something happens.
Yeah, I forgot about sigma.
Let's get some other questions. Alex Lazarian.
Andrei, I have some issues with understanding the importance of tearing instability in the connection in your settings. You pointed out to us very clearly that we have in the systems that you considered strong turbulence, and in this case, I just wonder whether we need to appear to any tearing process to explain fast reconnection and the ejection of energy or transfer the energy to other forms from magnetic field, because we know that in the 3D systems, even without any tearing, we have fast turbulent connection.
Yeah, you are talking about these colliding waves.
No, I'm not talking about the colliding waves. I'm talking about your earlier slides where you were talking about the magnetar system or whatever dipole system you mentioned, which is disturbed and becoming
okay, you mean this kind of situation?
Yeah, earlier situation, earlier. Yeah, I'm talking about this situation. I'm just saying that in 3D, you don't need to wait for tearing. And in any case, tearing is even different in 3D and 2D. And I just wonder, my question is simple. I just wonder to what extent your modeling depends on the particular tearing mechanism that you invoke, or it can be also applicable to a more generic, I would claim, in this situation, 3D turbulent connection.
Yeah, so we're actually working on 3D because it's a global simulation. So with sufficient resolution, one can hope to see well the details about how exactly the magnetic energy is released here, like how the opposite directed field lines eventually annihilate as they snap back here. So it is reconnection process, right? Tearing should be, I think, at some form at work there. But of course, when you look at this kind of setup, especially when you treat it like I treated it, so here in this problem, I must say, I must admit that for this particular calculation, the simulation of the pair creation, it doesn't matter whether you have it through tearing or someone else. All you have in this problem is the amount of energy, the value of magnetic field, basically, and the time scale for annihilating it. That's it.
Okay, I'm just, would like to attract your attention that in non-relativistic cases, when you start with initial tearing in 3D, eventually you come to the turbulent connection where tearing is not present. And in any case, you don't see plasmoids in 3D. I'm talking about
yeah, of course,
non-relativistic. Yeah, it's a different. It's very degenerate case to have the field light bite itself twice. It's just at some angle, and therefore it's three-dimensional loops, structures, which eventually, as at least in non-relativistic case, we can show that it results in Kelvin-Helmholtz instability and turbulence, and eventually there is no effect of tearing.
Yeah, I wonder if, well, I don't, maybe it's the wrong time for this discussion, but I guess at some level, even if you turbulence and you have these plasmoids, instead of forming regular chain, you turbulence this environment, you probably still have current sheets which collapse to the
We have current sheets, but the time scale for the editing over this, cascading energy from the scales is shorter than the developing of tearing and stability. I actually apologize. I missed our time for the discussion.
Yeah, that's okay. I saw your email, but it was also too late. I mean,
Yeah. But is it possible to talk with you sometime later?
Yeah. Maybe not. I don't know if maybe not today, but
Okay, well, we can anytime, maybe tomorrow. Well, maybe on Monday is fine.
Monday, of course. Yeah.
Okay, fine. Thank you.
Let's get the last question. Misha Medvedev, virtually visiting us from Kansas.
Misha is also here.
Hi, Andrei.
Hi, Misha.
Yeah, actually, I have a question. I need some clarification here. If you go back to the slide where you've been showing the dipolar magnetosphere and Dolphin waves propagating there, that's in the beginning of the talk.
This one?
Yeah, I guess here that's the movie when waves are propagating. I'm curious how Dolphin waves propagate perpendicular to the field.
No. The group speed is, of course, along the field lines. The reason why you populate different field lines is because the Starkweek, actually, it's the full simulation, which includes the crust. And so what Ashley did, he triggered the Starkweek at the bottom of the crust at some location here, and then calculated fully the dynamics of crustal oscillations. And so the first thing that you find before even you launch all these alpha waves is that the shear oscillations spread and populate the crust. And so with time, more and more crust is engaged in the oscillations. That's why you see, so there is no leakage of.
So you have your source of the fade waves at the crust, and
because as you can see, the polarial field lines don't even move, and it was exaggerated in this particular simulation. It was actually very nailed. It's not the full simulation is shown here. So Yaji did the full simulation, like force free. But here the field lines were even nailed, just kept apple, and the waves propagated in the approximation of linear dynamics. So by construction, there was no leakage.
Okay. Thank you.
I'll use my right as a host to ask the last question. Andrei, in this precession picture for FRBs, the precession period scales with the period of the magnetar. Over what time scale do you predict we will see change in the period, because the magnetar should spin down and the period should increase as the precession period should increase as well?
Yeah, that's a good question. We're thinking about the change of this period, and tried to, and Andrei Beloborodov pointed out that this should be changed. So we had some discussion almost a year ago, and then we decided that maybe we should wait a little more data, and you can make a prediction and you can test with more data, but I don't know if there is enough data by now. Okay,
so over the next few years, we should know better.
Yep, hopefully. And there is another object like that now with 156, maybe with less. I don't know how nailed that result is, but it looks also interesting. Half a year period.